Hello, everyone. Let's go ahead and get started. My name is Irina, as before. If you have any questions throughout, please let me know. So a brief review of what we talked about last time. We talked about different standardizations and regularizations for linear regression. In particular, we had discussed the subset selection methods, where essentially what we did is we built a collection of models with one variable, two variables, all the way up to p variables. We talked about different ways how we can choose best model with a certain number of variables. And where we stopped is when we compare models with different number of variables. Which criterion do we choose? Can you hear me okay there? You're good? Okay. So the reason this is important, again, is because if you fit the model with a larger number of variables, it's going to fit better and better. So you're going to overfit. So there are different ways you can compare the models between different number of variables. And what we discussed is that you can try to adjust for the bias due to overfitting, or you can directly estimate the errors using a validation or cross-validation approach. And we will discuss both next. So first, there's criterions that are called CP, AIC, BIC, and adjusted R-squares. And all of those criterions are essentially trying to account for the bias due to the different number of variables across these models. And as a recall, we talked about the credit data set last time, where we want to, just to illustrate again. So here's the credit data set. And what we have here is we want to predict the balance on the credit balance using 10 predictors: income, credit limit, credit rating, number of cards, and so forth. And what we also did last time is we found best models of different sizes. So best model with one predictor, with two predictors, and p. And what we're asking next is how do we select among these p models, which ones do we choose? So here's an example of how this may look before I discuss the criterion in more detail, using CP, BIC, and adjusted R-square. So all three of these metrics give you a score for each of the models, and then you select the one that minimizes the score. So based on CP, you will select a model with 6 predictors. Based on BIC, the model with 4 predictors, and adjusted R-square, I think it selects somewhere around 7. And the thing to notice here is that when you go between 4 and 10, there's not a lot of change that you see in those scores. In other words, the models between 4 and 10 are roughly equivalent. So first, what is CP? So the idea of the CP is that it takes your residual sum of squares, which you would normally use, but then it adds the correction to account for the number of variables you have in your model. So let me write this down. So I have, it's called Mallow's CP, or CP for short. So you have 1 over your number of observation, residual sum of squares, plus 2d sigma head square, where this extra term is adjustment for model size d. So in other words, the larger is the model that you fit, the more predictors, the larger is the d you have, the higher is the penalty. So at some point, this term is going to dominate the residual sum of squares and prevent you from selecting the model that has too many variables in it. The AIC criterion is similar, but it's more general. So in particular, the AIC criterion is defined through the maximum likelihood. And what you have here is that minus 2 log likelihood plus 2 times the number of variables in your model. So let me write this down. Oops. Oh, sorry. Thought I had a mistake. Yeah, so we typically want to maximize the likelihood, which means minimizing minus log likelihood. And essentially the idea is that both of these criterions have something that measures the fit, either the residual sum of squares or the likelihood, and they have an extra term that adjusts for the model size. So it prevents you from just selecting the largest model due to the fact that it fits the best. Moreover, in the Gaussian case, these two terms are essentially equivalent, because in the Gaussian case, your residual sum of squares correspond to your log likelihood, and sigma hat is the estimate of the variance, the maximum likelihood estimate of the variance. So in a Gaussian case, which standard linear models, that's essentially what we assume. Using CP is essentially the same as using AIC. But AIC is more general. So to prove this, the only thing you need is to recall that the Gaussian likelihood is essentially exponential sum of squares. And so if you take a log, you get the sum of squares back. So to maybe write it. So Gaussian log likelihood is going to be proportional to 1 over, well, actually to minus 1 over 2 sigma hat. Sorry. Oh. Here we go. Y minus x beta hat squared. Okay, so this is your residual sum of squares term. And then this multiplying by sigma hat on both sides. So you get residual sum of squares for the likelihood, and you get the sigma squares. So hopefully you can see that those two things are the same if your likelihood is Gaussian. If not, then they're not the same. Okay. So BIC is a little bit different. So we discussed CP and AIC and how they're equivalent. BIC has the same idea. So you have the residual sum of squares, which is a measure of fit, plus an extra term. But the extra term looks different. There is an additional log n up front. So you can do that. Again, recall the CP. You have residual sum of squares plus 2d sigma hat squared. BIC have residual sum of squares, but instead of 2, you have log n. Let's see. So I'm trying to highlight the differences. And since log n is going to be larger than 2 for n greater or equal than 3, essentially what it means is that you select smaller model with BIC. In other words, the penalty, the second part that penalizes the large models. So D, again, is the size of the model. For BIC, the second part is even larger. So it's going to try to select smaller models. And if we go back to the credit example, if you compare CP and BIC, you see that that's exactly what's happening. For CP, you select the model with 6 predictors, where BIC selects a smaller model, selects a model with 4 predictors. So if you are choosing CP and BIC or AIC and BIC, then keep in mind that BIC is always going to select somewhat smaller model than the other one. And this is the term that's driving this. Okay. So adjusted R-square is another criterion that's often used. Again, it's trying to adjust for the number of variables. And the idea here is that it looks kind of like the R-square, but a little bit more involved. I'm not going to write the formula here to repeat the formula, but I want you to again notice that rather than taking just the residual sum of squares and dividing it by n, it adjusts for the number of variables in the denominator here. So in other words, when we took a CP, we always just divide the residual sum of squares by n. When we look at the adjusted R-square, we divide by n minus d. So the larger is the d, the smaller is the denominator, the larger is the whole thing. And for the R-square, unlike CP, AIC, BIC, you want a large value. So it's kind of like an R-square that indicates the proportional variance explained, but it indicates it in a way that takes into account how many variables you have in the model. So if your standard R-square, not adjusted, just standard, it will always increase the more variables you put. The adjusted R-square does not necessarily do that, and again, the key here is the denominator. You have d in the denominator, so you take the number of variables into account. Or in other words, the adjusted R-square pays a price for the inclusion of unnecessary variables. And again, to see how it does, so you see when you go to 2 and then 3 and 4, it increases. It looks pretty flat between 5 and 10, but if you were to zoom in onto this graph, the maximum is achieved actually around 7, and afterwards it starts decreasing. It's not just keeps increasing, and that's because it starts to pay the price for those extra predictors. Of course, when you have several different criterions that give you different answers, a natural question is, well, which model should I use? And the answer is because all of these criterions give you different answers, you should be really careful with which model you choose. And how you choose it depends on what is the goal you have in mind, whether you have any prior knowledge of your predictors and so forth. If you will go for the simplest possible model, then BIC is typically the criterion you would pick, because BIC always going to give you the smaller model. If, however, you want to incorporate a larger number of predictors, or willing to take into account larger number of predictors, then CP or adjusted R-square may be better. Ideally, in your data analysis, you would say that you have tried these different criterions. All of them had similar values for the number of predictors between 4 and 8 or 4 and 7. We report the model with 6 as the one given by CP. So yes?
How about the AIC?
So AIC and CP are the same on this example because it's the linear model, Gaussian linear model. So if it's not Gaussian, then you wouldn't use CP. You would use AIC. So essentially, if you have linear regression, CP is the same as AIC. If you have logistic regression, you wouldn't look at the residual sum of squares, but you would look at AIC. So you can think CP for linear models, AIC for nonlinear models. Does that help?
Yes.
Okay. Any other questions? Yeah.
You said linear model is Gaussian model. What do you mean by that?
So thank you for your question. Let me clarify. So when I talk about the linear model, I mean we model our response y is beta 0 plus beta 1 x1 plus beta p xp plus epsilon. And you can put the I for the sample. And by Gaussian, I mean that the epsilons are normal with some variance sigma square and independent. So this normality is the key. Because essentially when I write the likelihood for this model, the likelihood is here with respect to epsilons, which are estimated by the residuals. And that's where this comes from. Okay. Does that help? Okay. So we talked about CP, we talked about AIC, BIC adjusted R-square. All of those methods are trying to adjust for bias. So let me do this again. Or they're adjusting not so much for bias, but for overfitting due to increasing model size. So the rationale here is the more predictors you pick, the better you're going to predict on the training data. And so they're adding this extra factor that takes into account the model size. And this is AIC CP, BIC adjusted R-square. Now the second approach, and a complementary approach, is try to estimate the error on the test data. And this could be done, generally speaking, through the validation set or the cross-validation procedure. And I'll show you how to do both in R. So again, what you will do is you will have a sequence of models, M1, M2, M3, and so forth. You want to select one model out of that sequence, and you want to select it based on the error you will expect on the test data. And what you do is, rather than calculating the criterion, you try to compute either the error on the validation set or the cross-validation error for each model. And then you select the model for which the test error is the smallest. The advantage here, there are several advantages. One of the advantages is that it doesn't require to estimate the error variance. So for example, if you look over here, for the CP BIC, you need to have an estimate of the error variance. And this may be unreliable. So that doesn't require you to do this. Another advantage could be, let's say you're using AIC. So for AIC, you're using the likelihood. So you're assuming a particular form. Maybe that form is incorrect. Maybe your likelihood is not a good measure of fit. With validation and cross-validation, the actual model you used to fit the data doesn't matter. What matters is how good is the prediction. That's the only thing that matters. It's taken more machine learning approach rather than modeling approach. Okay. So I'm going to show you first the pictures that you can get by doing this from the credit data example and how it compares with something like BIC. And then I'm going to show you in R how can you do this in practice on the credit data set. So the idea is this is on the left what we had from BIC. We had 4 predictors. If we do validation or cross-validation, then it will give us something around 6 predictors. So again, we may get a different answer by doing this procedure. But as before, the models between 4 and 8, they're roughly giving you the same answers. So you see again that there is a set of models that are very similar in terms of all the criterions that you consider and in terms of whether you do validation or cross-validation. Okay, so we're going to go to R, and I'm going to explain the validation first and the cross-validation second. So maybe let me give you a picture illustration first, and then show you the code. Suppose you have n measurements in your data set. You have n samples. Still not good with this technology. The idea of the validation set is that you're going to take your n samples and you're going to split it into 2 parts. One is going to be your training data, and the other one is going to be your validation data. Typically, you want to split it in such a way that you have more for training than for validation. The split that I'm going to use is I'm going to use 2/3 for training and 1/3 on the validation. And then the idea is as follows. I'm going to fit all models using training data only. But I'm going to evaluate all errors using validation data. In other words, I do not use my validation data when I fit the models. Okay? So how do you do this in R? So let me first make sure that we have our library leaps. As a reminder, this is the library that we use to do the best subset selection, forward selection, and backward selection. And what I'm going to do now, I'm going to split the data into the test and train. So the split here is a random process. In other words, I select 2/3 of the samples in the train and 1/3 in validation. So depending on the ones that got in the train, I got a different answer. Because I want my results to be reproducible, I'm going to set a seed first so that the split is always the same, no matter how many times I run this code. The way I do it is I take 2/3 of my sample size n, which is 400, and 2/3 on 400 is not a round number, so I round it. And then I sample from my n data points randomly 267 subjects. Okay. And I call those subjects my trained data. And now when I do the best subset selection, when I fit all these models, note that I only use that part of the credit data, those samples that ended up in the train. So before, I used all of them. Now I only use the ones that are selected by train. Okay. What I want to do next is I want to calculate what the errors are from all of these models on the test data. And in R, if I want to select all the data that's not trained, I can use a shortcut minus train. That's just a trick to do a different subset. So credit train with credit minus train gives me the full data set credit. The trick that I'm going to use is I'm going to form a model matrix. Essentially, it's the X transpose X. Well, it's just the X matrix that I need for this data using model matrix in R. This is just convenient for the prediction that I'm going to do. what I have considered, so let me remind you what's happening here. So what I have model of size 1 with just rating, model of size 2 with rating and income, model of size 3 with income, rating, student, yes, and so forth. And I have considered models up to size 8 predictors. And these models were built based on the training data only. And now for each of these 8 models, I'm going to calculate what the error is on the test data. So essentially the way I do it, I loop over the 8 models. For each one, I get the coefficients from that model fit. I calculate x beta for my test data, and I calculate the error as the mean of y minus x beta. So maybe a little bit more precise. So I get train, I get beta hat. Test, I have x test. So, and I have beta hat for each of 8 models. And then what I do, I calculate, actually call it test, not to confuse you, I meant validation. So I calculate, I take y validation minus x validation, but beta hat. I take the sum of squares for all of them. Actually, not sure how comfortable you are with matrix norms, so maybe I'm going to do it this way. So for each subject in the validation data, I compute the error of the fit for that subject. I sum it over all the subject in the validation data, and I take the average. Okay? So beta hat, again, comes from the train. Let me do this. But this comes from validation. So let me show you what it does. So after doing this in R, what I get is the plot. And you see that for the model of size 1, the errors are pretty large. 2, they decrease. 3, they decrease even further. But after 3, visually, you cannot even see the difference between those models. I think 5 or 6 is where the minimum is actually obtained. Okay. Are there questions about the validation set approach? Okay. So another approach is called cross-validation. It's very similar. Computationally, it's more involved, but I also like it because it's a little bit less dependent on how you split your data. The idea is as follows. So let's say you have your y and you have your x. So y is a long vector and x is a matrix. And here, rows are the subjects, 1 to n. So before, when we did the validation, we just did a 1 split, and we picked some for the train, some for the validation. With cross-validation, we are going to do k splits of roughly equal size. They're sometimes called k-folds, which is sometimes why it's called k-folds cross-validation. Typically, people choose k equal 5 or k equal 10, depending on how large is your training data. So what you do is you essentially divide your data into k parts. So for example, this is 1, this is 2, this is 3, this is 4, this is 5. And consequently, you treat each one of these parts as validation, and the remaining 4 as training. But rather than doing it just once, you alternate which part serves as validation. So essentially, you do the split into training and validation 5 times. But rather than doing it randomly 5 times, you do it in a way that essentially each observation had a chance to be in a validation data and to be in the training data. Okay. So let me show how you do this in R. Again, I'm going to set the seed so I split into folds. And I'm going to select to split my data into 10 folds because I have a pretty large sample size. The trick I'm going to use is this command, and the code will be available to you. There are packages you can use to do cross-validation. I've seen people coding it in a very inefficient way. You only need 1 line of code to do it, just so that you know. So essentially what I'm doing here is I'm creating a vector that I call fold ID, which assigns a particular fold number to each observation from my data set. So I have around 400 observations here, 400 rows of data. And with this one line, I get a number from 1 to 10 randomly to each of those observations in such a way that roughly, actually in this case exactly, I have the same number of observations in each fold. Okay? So what I'm going to do next is very similar to what I did with validation, except now instead of having a vector of errors, I'm going to have a matrix of errors. Because I'm going to consider 8 models as before for each of the k folds. So it's like doing 10 times what I've done before. Okay. And so what I have is that I have an outer loop over folds where at each fold I set my training data to the ones that's not equal to that particular fold and test otherwise. And then for each one of train and validation, I do exactly the same code as I had before. So to illustrate maybe a little bit better, I'm just going to show you what happens for one fold manually before I run it. So let's say I take fold being 1. Then essentially what I do with train, I pick all the numbers, all the observations from 1 to n that were not assigned 1. So in other words, I'm choosing folds from 2 to 10. And what you get is ID for all the subjects that were not assigned fold 1. There are 360 of them. I use this 360 subjects to train my model, and the 40 that were in the first fold to test my model. And I calculate the errors the same way. So as a result, what I have is a matrix where the number of rows is the number of folds. So here the first fold was the validation. Here the second fold was the validation. Here the third fold was the validation, and so forth. Each column is the model of size 1, 2, 3, 4, and so forth. And the results of that, you can see that for each fold, the numbers are slightly different. So that what I do last is I average across the folds. Okay. And what I get is actually a picture very similar. It's a very clean data set. no matter how you do it, you're going to get pretty much the same answers, that the models between 4 and 7 look very, very similar. 2 is definitely not enough. 3 is getting closer. At 4, I would say you're already picking most of the signal in this data. The advantage of doing the cross-validation over validation, again, first advantage is that all of your observations get a chance to be in a validation data. All of your observations get a chance to be in the training data. The second advantage, because you're repeating this several times, whatever is the number of folds, then by looking at this matrix of the cross-validation errors, you get an idea on how the error change when you change your validation and validation and training data, but keep the number of observations the same. And this gives you something about the variability of your selection criteria, and you can actually use this to get some idea on how confident you are in the model that you have selected. So again, to conclude, the validation errors, we just split the data once and treating one part as validation and the other part as train. The cross-validation, we use 10 folds. And here, visually, you cannot see the difference between 4 to 7, I would say, 4 to 8. But if you actually zoom in and find the minimum, both of them would agree that model with 6 predictors is the best. What you can also do, so before I go there, first that all approaches suggest, so whether you adjust for the bias using BIC, AIC, or do this, you can see that 4, 5, and 6 variable models all give you roughly equivalent answers no matter which metric you use. And that's important to report so that you just don't pick the model you like the best. And going with the idea of cross-validation, you can select the model using one standard error rule. So what I mean by that is when you go and look at your cross-validation errors, you see what's the variation from one fold to the next. And you can use this to estimate the standard deviation associated with this error. And so rather than selecting the model with a minimal average error, you can select the smallest model that's within one standard error of the minimal one. I'm not going to go into the details of that, but I just want to emphasize that it gives you this information on variability that you can use to your advantage. Are there any questions about the cross-validation or validation approaches? Yes?
So cross-validation doesn't improve the model, but it helps in getting a better result.
None of these methods improve the model.
Just for selecting this.
It's the selecting the model, yes. So the idea, again, what we have discussed so far is that you may want to modify your original least squares. And one way to modify it, which we have discussed, is to do subset selection. In other words, don't fit it on the whole list of predictors that you have, but only on a subset. And the key thing when you do the subset selection is you need to first figure out best model of given size. And this is what's going to give you M1, M2, M3, up to MP. And what you need to do next is figure out which size model to select. So last time we talked about this part. And today we talked about this part. Does that helps? Okay. Any other questions? Yes.
Go back and explain
No, the rows were the folds.
Okay.
The columns are the models.
Okay.
So essentially what you have, let me do the schematic again. Or maybe, actually, I can do it here. Can I do it here? No, I cannot do it here. Let me do the schematic. So cross-validation. I like pictures if you didn't grasp that yet. So you have your first fold equal validation. Then you have second fold as your validation, and everything else training, and so forth up to the K fold. And then on the columns you have model of size 1, model of size 2, model of size 3, model of size 8. And everywhere here you have errors. And what you do then is you average across columns to get the mean error across the folds. Any other questions? So another idea what you can do, so that was the subset selection method, is you can do some shrinkage. And the idea of shrinkage, the most popular methods are ridge regression and lasso. Lasso could be viewed as a subset selection method as well. But the idea is that instead of necessarily selecting a subset manually like we did here, you're trying to constrain or regularize the estimates. So the schematic that I gave you last time is that here's your model again. With least squares, you get a set of solution, set of estimates. With shrinkage, you're not necessarily going to get a subset. But you are going to get a different estimate. And they can be viewed as the original one shrunk towards 0 or modified in some way. And this tends to help with the fit and help with the errors quite a bit. So how do we fit the least squares? What's the idea of modification? Well, we fit the least squares based on the residual sum of squares. We evaluate the error as the squared error between the response and the predictors, and we try to minimize the squared error. The idea of the ridge regression, which is the first way to shrink the coefficients, is to regularize the beta or add an additional term within your optimization perspective. And this additional term is the Euclidean norm of your beta coefficients, so sum of them squared. And the weight of that term is determined by lambda, which is a tuning parameter. So again, to write this down, ridge regression, you have your residual sum of squares like in your standard least squares, but now you have an extra term where the lambda, non-negative, is tuning parameter. In particular, if it's 0, then you get just standard least squares. And why does this lead to shrinkage? Well, if you didn't have the residual sum of squares and you were just minimizing the second part, it's non-negative because it's all of them squared. It's minimized when it's 0. So beta equals 0 minimizes the second part. The first part, the residual sum of squares, does not want beta to be 0. So by combining them two, you're shrinking whatever coefficients you will get from the residual sum of squares towards 0. And how much you shrink them depends on the magnitude of your tuning parameter. So again, it tries to estimate the data well. And the reason for that is because it has the residual sum of squares term. However, the second term, which is often called a penalty, or more specifically is shrinkage penalty, encourages those coefficients to be close to 0. And again, it encourages them because we're minimizing this function. This is non-negative, so it's going to be exactly minimized when all of them are 0. And so as a result, your parameters, your estimates are shrinking towards 0. The tuning parameter, as I said, it controls the relative impact, and it needs to be selected. So how do you select the tuning parameter? Well, you can use the same techniques of cross-validation and validation that we have discussed. Because essentially, in this context, we're changing the problem of selecting the model size to the problem of selecting the tuning parameter. So the idea will be as follows. You will consider a sequence of tuning parameters and then which one to use. You can do cross-validation or validation with each one of lambda i's, and then pick the one that minimizes the error. So the beauty of cross-validation and validation approaches is that it's very, very general technique. You don't have to have a linear model in mind. You don't have to have a subset selection in mind. Whenever you have any kind of parameter that you need to select, whether it's the tuning parameters here or the subset or whatever, you can just split your data into validation and train, fit the model with each of these values, and then select the one that minimizes the error rate. So this is an example for the credit data. And due to the limited time, I'm not going to show the R code, but I want to explain what's happening. So this is the tuning parameter lambda, and it varies from something that's really, really tiny, 1e to the minus 02. You can think of it as 0, to something that's pretty large. What this plot shows, essentially, if you take a cut through this plot like this, then the values that you get on these lines are values of estimated beta tilde with that value of lambda. So what it says is that, for example, the red line here is limit. And what it tells you is that if you fit the ridge regression with lambda somewhere between 1e to the minus 01, then for limit, the coefficient will be around 400. For rating, the coefficient will be around 200. For student, the coefficient will be around 100. And for income, around minus 300. By looking at this plot over lambda, you now get to see what the effect of increasing the lambda is. And what happens is that all of those coefficients, some faster than the others, start to go towards 0, or they get shrunk. And at some point, when your lambda gets too large, that second term is way overpowering. So essentially, everything gets set to 0. When your lambda is really small, then over here, so all the way to the left, you essentially get your least squares. Here, you get 0. And so lambda gets you somewhere in between. A key thing that lambda does not set anything exactly to 0 unless you go towards the end. But it does shrink the magnitude. So the magnitude, as you move, for example, the magnitude of the coefficients here, in absolute value, they're all smaller or closer to 0 than they've been at the beginning. Okay. What the second plot here shows, oh, I think I'm out of time. Well, just one thing. It's the same plot, but rather it's what the value of the coefficient of the ridge versus the original least squares. And essentially, okay. So it's the reverse picture of this plot. So this one goes this way, and this one goes this way. So when it's least squares, then they're exactly the same. And as the lambda increases, the ridge becomes smaller, smaller, and smaller. So it's a different expression of the magnitude, how the magnitude shrinks. Thank you very much.